Hello, my name is Taylor Hyman,
I'm Joel Eberhart.
I'm Dan Rodonick.
I'm Austin Walton.
and today we're going to be talking about the air-cooled insulated camping tent. Here in the pictures below, you can see that this is what our final product come out to be for this semester. And we're going to be going into the introduction of why we did all this stuff, and also the customer needs, and the analyses, and also the beta and alpha prototypes, and also the costs and the scheduling for this semester that changed a lot, which we'll go into that later on, and then also our next steps. So here for the introduction, we looked at the problem in the world. We saw that heat was a major issue when coming to outdoors, and also that there's hundreds of heat-related deaths in America per year, and also that just keeping it comfortable while being in a tent overnight. Here we're looking at the customer needs, and once again, we just wanted to make sure that the customer was able to sleep comfortably in the tent in the 65, 70 degree temperatures without being all sweaty, and also the durability of the product, and also being efficient to drop that temperature down, and also the cost and quality. We didn't want the parts to be really cheap, so that would really build into that higher quality. And also the capability to transport the product. We didn't want the product to be very heavy, so that would make it easier for our customers. Here's our preliminary design goals. We done these before we even started analyzing things. We see that we were being able to cool the tent down from 85 to 70 degrees, and also having a cooling load of 3,000 BTUs. Also having the tent be insulated to be able to keep that cool air in, and create the battery power air cooling unit as a whole, and using a cooler that the customer can also use to put their food and drink in. And also the ISO. We did some research on this, and we saw that there needs to be an opening of 100 centimeters squared per person, and we'll talk about it later in this presentation.
So last semester for the analysis we conducted, we did the IESBE analysis of the tent geometry, which is an engineering software used by McClure engineering firm out of St. Louis that does HVAC for buildings. And we used it to find the cooling load required. The governing equation for this is Q is equal to the change in temperature over the thermal resistance. Next, we also look at the thermodynamic cycle of cooling inside the system, and we use this to find a cooling load for specified components. And the governing equation is Q is equal to mass flow rate times the change in enthalpy. And lastly, we analyze the heat exchanger providing cooling. This used to find the output cooling load of the heater core, and the governing equation was Q is equal to mass flow rate times the specific heat times delta T. Some of the results that we got from our analysis is our cooling output would be 6,645 BTUs per hour. The insulation that we would be using is R8, and we would be receiving 1,046 BTU per hour from the outside, and that includes 2 people inside the tent. The ice depletion, we would require around 60 pounds of ice per night with 2 people inside the tent. The system would run for 9.5 minutes total per hour. So after all the cycling's done an hour, it'd be 9.5 minutes. And after all this analysis, we decided on some improvements for our system. So originally we're going to have some copper pipe run through the cooler, and effluent would flow through the copper pipe, and it would dump the heat into the cooler into the ice. And we decided to go with pumping the ice water straight into our system. So for our alpha prototype, we will be using a standard tent. We wanted to see how well a standard tent would keep out the heat versus our beta prototype when it was insulated. We would as well be using the air handling unit, which consists of a box, a heater core, sheet metal, fan, water pump, battery, thermostat, vinyl tubing, and thermocouples. Those white wires you see in the video coming out are the thermocouples, how we measure the temperature of the water and the airflow. And lastly, we'll be using cooler with the ice water. All right, so for our alpha testing results, we end up receiving a cooling load of 5,200 BTUs per hour. If you gentlemen want to know how I received this, then just let me know and I can go more in depth later on. The ice depletion. So it's important to understand our system was running nonstop, and we burned 7 pounds of ice in 19 minutes. This is 19 minutes straight of runtime, and in a normal setting, it will cycle on and off. So our cycle frequency without the insulation, the initial cool down was 3 minutes and 40 seconds. It was off for 1:50 and on for 1:50, and it continued to do this. And it would average out to 1:50 on and off. And our battery longevity is about 6 hours of continuous runtime. If you gentlemen look to the graph on the left, this is our BTU per hour over time. The blue represents water and the orange represents air. So this graph really makes sense in the fact of a room has cold and hot pockets of air, and as the air is stirred up and mixed, you'll have higher and lower temperature, and this reflects in it going up and down in the orange with the air. And as far as the water, once everything starts up, you have to cool down the system, and this is why you have such a BTU and high BTU per hour. Is there's a high change in temperature, and once everything's cooled down, then it levels out, and it shows this in the graph where the blue kind of levels out.
So for our beta prototype, this is the video that you can see on the left here is a time lapse of how the tent panels were actually made. There was 4 panels total, and those each have 4 sub panels inside of them. We used the wall insulation that was R13. We peeled that in half, that made it into R6.5. This is the most cost-effective way that we could get something that was close to R8, which was our goal to hit originally. There was a lot of different issues that we ran into before. We tried to use a sewing machine, that didn't really work out. And then whenever we made these panels with the duct tape instead of the sewing material, we had to use an adhesive spray to keep the insulation inside the panel so it wouldn't fall down and just not end up with a trash bag tarp full of insulation. Our air handling unit for the beta prototype was also the exact same as the alpha prototype, just because of all of the delays and stuff like that that we had with lack of manpower due to COVID-19 and all that stuff. The cooler was the exact same. And then back to that ISO standard that we were talking about before, we needed 100 square centimeters per person inside the tent. Our tent blows that number out of the water with 4,200 squared centimeters. And that's adjustable for the customer's needs as well, so that the oxygen depletion is no longer an issue. That was something that we talked about in our last presentation, so that the customer can adjust it the way that they need it. So this was our beta prototype testing tent setup. We had to throw the cooler inside the tent because only one person could be testing at a time, just because of our manpower issues due to COVID-19. Normally the cooler would be on the outside of the tent and everything would be sealed up really nice, but we had to have it inside so we could weigh the ice while it was running. And you'll see in the later slides how our heater was set up on the outside of the tent and how we set up all of our ambient conditions and stuff like that. You can see the thermocouple wires measuring the inlet and outlet water temperatures into the heater core. And then this white wire up here for the thermocouple goes to the top of the tent outside, and that just takes the ambient conditions on the outside of the tent. And as you can see, the 5-gallon buckets in there were how we weighed the ice. We had to throw the ice in there, weigh myself with the ice, and then weigh myself with empty buckets on that scale, and that's how we did that as well. This is how we had our heater set up. We had a 10 by 15 garage, and the heater allowed us to bring our ambient conditions up to the temperatures that we needed, which was about 87 degrees, just because our outside temperatures were not ideal for our testing. And I had to seal up the garage and pipe out all the flues for that as well, just to make sure that we didn't lose a bunch of heat. So this is our results from our beta prototype testing. Because we only ran one continuous test, and one person can't be in that tent by themselves trying to test all of this for an extended period of time. We only went for an hour and 13 minutes, but we got a solid set of data proving that our concept and our prototypes work really, really well. It would only run for about 30 seconds and it would kick off. The pull down time to get from that initial ambient outdoor temperature to keep that tent down to 70 degrees was only 2 minutes. We lost about 4 pounds of ice during that as well. And then the normal cycle, 30 seconds on and then 20 minutes off. It stayed off for 20 minutes, which just goes to show that the insulation for the tent was really well put together. And we only lost about a pound of ice per cycle. That also kind of had to do with the cooler was propped open. Normally it would be piped in. We'll get into that later with our actual production model. We went ahead and took a decibel reading just to make sure that the conditions inside the tent were good enough for someone to sleep. And we got about 52.3 decibels, which is pretty standard for how someone would sleep. It's in the range of 60 to 40, which is what is considered sleepable. So here's our specification chart. This is just a really good summarization of the last 2 semesters and all of the numbers that we got from them. I'm going to glance over this really fast, but there's a lot of numbers here that are really important, and some not so much, like our tent base and height. None of that stuff really changed throughout our 2 semesters just because we used the same tent for the entire time. Our cooling load required, we were originally shooting for less than 3,000 BTUs. After using IES, we saw that it was going to be about 1,000, and it turned out to be even less than that, around 427 BTUs per hour. Cooling system output, same thing. The numbers just keep getting better and better as we go. And our insulation, like I said before, we originally wanted R8. The best thing we could find was R13, peel it in half, and we got R6.5. That ended up working out really, really well. And the costs along the bottom there are just the costs that we were shooting for just the prototypes, not the actual production model. We'll get into that later too. So as you can see here, this is our actual production model. Like I talked about before, the piping will be going directly into the cooler, so you won't have to keep the lid prop open and have heat loss there. Stuff that's not so easy to see in here, the insulation panels, those would actually be made out of the tent material, original, and out of nylon, and use sewing material and not duct tape and blue tarps. And the Velcro will also be sewed on. There was some issues that we had with assembly and disassembly of the tent. The adhesive Velcro that we used would kind of come off, but if it was sewed on there for an actual production model, the product that the customer would actually buy would not have that issue. The air handling unit, just because of lack of time and lack of manpower, our alpha and our beta air handling unit was exactly the same. Really, the only thing that was going to be improved was aesthetic stuff. But in our actual customer product, the ductwork would be symmetric. It would just look better. The box holding the pump and the battery would be smaller. The overall battery in general would be smaller. There would be ergonomic carrying handles so that the product would be easier to be manipulated and moved around inside the tent, and also easier to be transported. And then there would also be component covers, and all the sharp edges would be rounded off as well.
Here's our cost breakdown of the actual consumer product that we have. On the left, there is the breakdown of all the individual components going into the system. In the middle column is the breakdown of the parts assembled for the tent, the cooling system, and then lastly, we have the battery charger. That's just a separate component that will be bought. We estimated that for the air handling unit, we'll be able to make 2 per hour at $23 per hour. And then for the tent, we can make 2 of those at $16 per hour. And in the third column there, we have our total unit cost, our cost estimate and overhead. We will be producing about 3,000 units per year at manufacturer's suggested retail price of $9.99, and we'll have a final profit of greater than $1 million. Here's our schedule for this semester. All the stuff in green is stuff that had to be moved around due to COVID-19, and the stuff highlighted in red are things that we couldn't get completed in time because just time constraints, meeting constraints with the pandemic. But however, all the other stuff we were able to complete on time, still made a working system. All right, for our next steps, we really wanted to do further testing in multiple different conditions, environments with more humidity, higher temperature, and that stuff. And from that, we'd be able to complete an ice chart that would show the customer how much ice they needed to last in those conditions. And we also wanted to do a battery longevity with cycling. We were only able to do a small test of that, so we'd do a more complete, thorough test of that, and then just produce a more compact prototype. So in conclusion, we were able to show that we could build a tent that easily maintained 70 degrees Fahrenheit inside the tent with an ambient outside temperature of 85 degrees Fahrenheit. We were able to quickly cool down the tent with minimum runtime, and we're just overall able to provide a safe and comfortable camping experience for the end user. Any questions?